Hello everyone. So we'll continue with our discussions on the topic of shear center. Specifically in today's lecture, we'll look at a direct application of the theory that we had developed in the previous lecture. So in that previous lecture, we had mentioned and emphasized very clearly that the theory that we were developing had to do or was restricted for thin-walled open sections. So if we take a quick look back at the diagram that we had drawn earlier, so this was the kind of structural member that we were looking at. So in fact, this was our starting point. So we had a cantilever beam which was shaped like this. The two most important characteristics of this shape are that it is open-ended, so these two ends are not joined, and very importantly, the thickness of this structural member is very, very thin. When I say thin, it basically means that it is thin in comparison to the other dimensions of this beam. Okay, so the application that we are going to look at will be at a very specific variant of this kind of a thin-walled open section. And if you remember, we had mentioned that the motivation for taking up this kind of a generic figure here was basically to capture the in a very general way the important kinds of shapes which are commonly used in engineering practice. For example, an L-shaped beam or a channel shaped beam. So also an I-shaped beam or a T-shaped beam, Z-shaped beam. But in addition to those shapes, we can also have a beam which has an almost circular cross-section. What I mean by an almost circular cross-section is that instead of a complete circle, it will be open-ended like this. But instead of a general shape like this, it will be so this arc would be part of an actual circle. So that is the example that we would be taking up today. Okay, so this is the shape we are interested in. This is the shape of the cross section. A few important points to note. This arc here is part of an actual circle. Furthermore, this thickness is very small compared to the average radius of this circular shape. And what we are interested in doing here is to find out the location of the shear center. Okay, now we know that the location of the shear center is a purely geometric entity, meaning that it is completely independent from the kind of loading that this beam is imposed to. So it might occur to us that for the purpose of finding out the shear center, we really do not have to bother about the loading of the loading that is imposed on the beam, and that is true. We really should not be worried about any kind of loading, because as long as we are absolutely sure about a very specific cross section, we can be sure of the way of finding out the shear center. But that notion has to do with the mathematical theory behind behind the shear center. But in order to have a proper physical understanding of the situation, especially as it pertains to the concepts of the generation of the torsional moments as applied by the external load, and as balanced by the distribution of shear stresses, which we had time and again discussed in our previous lecture, it is perhaps more useful and informative if we actually consider an external load, a specific case of an external load, and then try to find out the shear center with regards to that. But I again emphasize that ultimately, whatever the answer we will get for the shear center, it is not going to depend on the load, and we'll see that. Okay. So what we do first of all is to set up our coordinate axis. Now, the moment we see such kind of a very regular shape, what I mean by regular is that it has some sort of natural symmetry to it. It is our motivation to somehow orient our axis aligned with those axes of symmetry. So, for example, this particular shape has a natural axis of symmetry here. So along this horizontal axis passing through the center, and our natural first temptation would be to set up our coordinate axis perhaps at the center of this circular shape, and maybe orient one of the axes along the horizontal axis of symmetry. Okay, suppose we do that. Suppose we set up our axis like this. So suppose let's say that our center is somewhere here, and we set up our y-axis and the z-axis like this. Okay. I want to have a clear-cut discussion about this, because in most of the textbooks you will see where they are solving problems, this discussion is not really exposed in an explicit fashion. So I'd like to have a clear-cut discussion about this. You see, if you remember what we had discussed in the previous lectures, we had mentioned that when we wanted to find out the location of the shear center, our first job was to find out the distribution of the shear stresses on a particular exposed section induced by a cut. And as we developed the theory, if we take a quick look back at that, we saw here that this shear stress, it ultimately, or maybe if we go back one more slide, so here we saw that this shear stress got expressed in terms of the bending stress, which was the sigma xx. Now, we had mentioned during the development of that theory that when we were finding this expression of sigma xx in the previous lectures on unsymmetrical bending, basically, so when we derived this thing, this formula was derived first of all starting with the y and z axis in such a fashion that they were centroidal axis. That is, the y and the z axis pass through the centroid of the cross section under consideration. So if we have to use this formula, then we must set up our y and z axis at the centroid, and this entire derivation of the shear center location was done keeping in mind that. Okay, so what are we doing here? You see, here we have put our y and z axis at the center of this circular shape. However, you note that the center here will not be the centroid, of this particular section, because a part here is missing. Had this not been missing, this would have been a perfectly symmetric annular cross section, in which case the centroid would have been at the center of this circular cross section. I repeat myself, if these two ends were actually joined so that the entire shape or the entire cross section here was in the form of an annular circle, then in that case surely this center would have been also the centroid of the cross section. But in this case this part is missing, which means that the centroid will actually be shifted a little bit to the left. You can, even without any computation, you can understand that, because this part, the counterpart here which is missing, it will kind of pull the location of the centroid here. But because of the symmetry about this horizontal axis, it will still be along this z-axis. So actually the centroid would be a little bit to the left of this center. So ideally we should be referring to the axis which are not this y and z axis, rather which are let me use a different color to denote that. Rather we should be denoting this thing by something like this. Okay. But I do not wish to delete the red colored y and z axis for a certain reason, which will be clear in a few minutes. Okay. So to resolve this confusion about the axis, what I'll do is I'll first of all write down the expression of the shear stress distribution, refer to the blue colored y and z axis such that the origin is actually located at the centroid of this particular cross section. So let me make this clear, that this thing is the centroid. So if I write down the expression for the shear stress, I can just look back at the previous lecture notes, and you see this is the one that I am interested in. So this is the entire expression, and you note that it does include this externally applied transverse load P. So we'll just write this down. So sigma xs is equal to sigma sx is equal to minus p divided by I yz square minus iy iz times, in the numerator we have iy qz minus iyz qy, where we again remind ourselves that qz is the first moment of area about the z-axis and qy is the first moment of area about the y-axis. Now, is it possible for us to have a bit of a simplification on this formula? You note that as I had already mentioned, this particular cross section, it has an axis of symmetry, which is this horizontal axis. So whether you take the red colored z-axis or the blue colored z-axis, they are coincident, and the axis of symmetry is along those axes. Now if we have an axis of symmetry, then you can immediately conclude that the value of Iyz will be equal to 0. So Iyz is the second moment of area. We know that Iyz expression is like integration over the entire area y y times z times dA. So because for every element which is above the z-axis, there will be a certain value of y, and there will be a counterpart element below the z-axis which would be having a location denoted by minus y. So when we integrate over the entire area, that it'll result in Iyz being equal to 0. So you understand that the way that we have located our coordinate axis, this blue colored coordinate axis, it so happens that the y and the z axis are also the principal axis. So we write that down here. Because of the choice of our axis, Iyz is equal to 0. Therefore, our sigma xs is equal to sigma sx is going to be equal to P divided by Iyz, where I have cancelled the minus that is present here with the minus that will be present here, this Iyz being 0. Iyqz, and here this Iyz is 0, and you note that again this Iy cancels with this Iy. So overall what we have is just Pqz divided by Iz. Alright, now you note that whatever we have done till now has been with reference to this blue colored coordinate axis, this y axis and this z axis. But ultimately, as a result of the inherent symmetry of the cross section about the horizontal axis, what we are ending up with is the expression of the shear stress, which involves the external load, but it involves only the first moment of area about the z axis and the second moment of area also about the z axis. So we do not have anything in this expression which is with reference to the y axis. So if we come back to this diagram and see that for a moment you imagine that instead of this z axis, perhaps you were actually referring to this red colored z axis, then would that make any difference to the resulting value here? I repeat, whatever we have done till now for this sigma sx or sigma xs, we have ended up with this expression, and it involves only things which are with reference to the z-axis. But suppose you say that no, I am referring the things with reference to this red colored z-axis, not the blue colored z-axis, then would it make any difference to the resulting value here? The answer is no, it will not make any difference, because of course y is different if we consider the red axis or the blue axis, but the z-axis is absolutely the same in both the systems. So whether you take the blue colored reference axis or the red colored reference axis, the quantities which are calculated with reference to the z-axis, they are the same. Why am I making such a big deal of this very niche point? You see, ultimately we have to find out the torsional moment. The torsional moment of the shear stresses which would be distributed over this thin member. Now, it is much easier to find out the torsional moment of the shear stresses which are distributed here about this axis which is passing through the center instead of this one. I repeat, when I ultimately find out the distribution of shear stress and I want to compute finally the torsional moment due to those shear stresses about an axis, about a longitudinal axis, it is far more convenient for me to have the longitudinal axis which is passing through this point, this actual center of the circular shape, rather than this one which is a little bit eccentric. Because you see, the distance of all these points which are lying here, they are the same from this, because this is the center of this circular shape. So fortunately, as a result of this formula like this, which depends only on the z-axis, I can move back from this blue colored axis to this red colored axis, and it will not make any difference. Okay, so even though we have used the expression for the sigma xx as derived based on the centroidal axis, but just fortunately as a result of this thing, we can move back to a pair of to an axis which is not the centroidal axis. Okay. So to go ahead with the solution of finding the location of the shear center, we'll take some very neat and clean steps. So the first step would be to find out this value of QZ for this section. Second, we would be finding out the value of this IZ. Now please note, even though I had been referring to this QZ as the first moment of area, we have to understand that this is actually like the first moment of area. So IZ is like a global property for this entire cross section. So IZ is calculated for the entire cross section, is the second moment of area of the entire cross section. But this QZ, it's like a local property. So every point where you sit here, when you sit here at different points of this member, the value of the QZ is going to be different. So it's like the first moment of area that is present over this, and this thing will be absolutely clear when we actually compute it. So the first two things that we'll do to find the location of the shear center. So first thing is to find QZ all along the cross section. Second is find IZ for the whole cross section. After we have done these two steps, what we'll need to do is come back to the expression of sigma xs is equal to sigma sx, because we already know the value of q and z from the qz and iz. From the previous two steps, we can find out the expression for sigma xs, the shear stress, and because the qz would be calculated for different points all along the cross section, the expression of sigma xs would also be dependent on the location that we are looking at over the entire cross section, which means effectively what we would be getting is a distribution of sigma xs along the cross section. So after we do that, what we'll need to do is so let's write this as the distribution. After that, torsional moment contribution and balance. So what do I mean by this? Again, referring back to our previous lectures, the shear stress distribution that we obtained in the previous step, that will enable us to find out the the contribution to the torsional moment over the entire cross section due to that distribution. And next, what we'll be doing is to balance that torsional moment contribution from the shear stress to the torsional moment contribution from the externally applied load P. And that will give us the location of the shear center. So let us proceed to find out the location of the shear center by following these steps one by one. So first of all, we are going to find out the QZ all along the cross section. Okay. So let's draw the cross section quickly once again. This time I'll locate my my z-axis like this. I understand that my y-axis will be like this, and this, I emphasize, is no longer the centroid. This is not the centroid, but rather it is the center of the circle, of the circular shape. Now it'll be perhaps easier if I just extend this a little bit more. So this is just for the purpose of clarity. Okay. Now because we are talking about a very specific cross section, we have to mention clearly what are the extents of these two ends. So those extents would be represented by this angle alpha. And as I have mentioned repeatedly earlier, the same angle alpha will be subtended by the end of the cross section, which is below the z-axis. So the angle that this end will make here, that is also going to be alpha. So let me make that clear. So this angle is also going to be alpha. Now I am interested for the purpose of finding the QZ all along the cross section at different points along the cross section. So I want to sit at different points here, all along this cross section, and I want to find out the value of the QZ. Okay, so how do I do that? If you remember what we had done near the end of the previous lecture, and we can quickly refer to that also. So it should be somewhere here. Okay, so you focus your attention here. This QZ was basically this thing, integration 0 to s y TDS. You note that the TDS represents the elemental area, but we are doing the integration from 0 to the particular location S. So the 0 represent one end of the open cross section, and this S represented a generic location anywhere within the cross section. So let's repeat that and calculate it in the context of this specific cross section. So QZ will be equal to, let's just write down the formula, y TDS. I again emphasize here that as we had discussed in the previous lectures also, this T is having the same value all along the cross section. It is possible to have a theory where this is perhaps varying, but that is just an extra complication without much return of investment as far as the physical understanding is concerned. So we'll just stick to this simpler case of a constant thickness all along the cross section. Okay, so how do we translate or how do we compute this particular thing for our cross section here? So what we'll do here is we'll take this generic distance S from this open end. So we'll start from here. We understand that S equal to 0 is present here, and we're going to move along this. So what we can do is just mark it out in this fashion. So this is S equal to 0 and this is S equal to S. So we are basically looking at a generic bit of the cross section which is like this. So you understand that as I move along the cross section like this, the area that will be covered will keep on increasing until I reach here where it will be the maximum. Okay. Now what about the Y part? So you understand that when I'm sitting at this zone, sure enough, if you zoom into that, the different points. So if I just draw a little zoomed in view of this thing, it will be like this. And you understand that the different points which would be lying along the thickness would, very strictly speaking, have different distances from the z-axis. So these different points would be having different y coordinate values from the z-axis. But again, you remember that this thickness is very, very small. That's the key point to remember here. This thickness is very, very small. So for all practical intents and purposes, the little variation of the y values for these points will really not matter. And what we'll do is we'll take some sort of an average distance from the z-axis. So this y that is present here, we are not going to strictly adhere, or we are not going to strictly talk about different points. Rather, we'll talk about some average point or some point which represents a typical point within this thickness. So if we say that the average radius of this section is capital R, so what we mean by that is, let's say that so if this is given by R, we are only going to look at points which would be located along this arc, which would be passing somewhere along the middle of this very thin cross section. So this y would be for a point which would be lying on this blue arc instead of anywhere else on this thickness. So now it becomes quite easy to write. What we can do is this S, you understand, is like this. So our S is going like that, and you understand that it will be easier to do the whole calculation if we just make use of the angles here. So let's say that we represent the angle here by a generic angle by phi. So S will be equal to R times phi. What we'll do here is we will denote this entire angle, that entire angle, by phi. So you understand that the expression that I have written here for, as S equal to R times phi should actually be R times phi minus alpha. Okay, but as far as the ds is concerned, it doesn't make any difference, this little difference of alpha here, because the alpha is a constant for this particular cross section, so it will be R times d phi. The ds will be R times d phi. You also note that the distance y will be represented in terms of these geometrical parameters, the capital R and the phi, as R sine phi. So for any generic point, the y will be R times sine phi. So just in case if that is not clear, you note that we have our arc like this, and this entire angle is phi, this distance is R, and this is our y. So this is the little bit that we are concerned here. So I've just isolated this bit here, and just to have it clear that y is equal to R sine phi. Okay, so now we are ready to calculate this. So integration R sine phi times t times ds. So ds is R d phi. And now you note that when we go from for the limits of s going from 0 to s, the corresponding limits for phi would be alpha to a generic phi. So okay, we have to be extra careful to note that phi does not start from 0, because the 0 for the phi is on this horizontal axis. We are not interested in any point there. We want to start from this point, which is s equal to 0. So s equal to 0 corresponds to phi equal to alpha. So you can understand this clearly from here. If s equal to 0, phi should be equal to alpha. So that's what we have used here. And any generic point s equal to s, that is just phi. So no problem there. So the upper limit is no problem. Okay. So this thing will be equal to, so we have r square going outside, because that's a constant, doesn't depend on phi. The t can also go outside the integration, that doesn't depend on phi. So what we are left with is integration from alpha to phi sine phi d phi, and that is nothing but r square t minus cos phi. We have to put the proper limits here. So it's like this, and the expression for qz turns out to be cos alpha r square t cos alpha minus cos phi. Okay, because this phi here represents a generic point here, that is why this qz is actually representing so the value of this qz is varying as we move the phi from alpha to this thing here. So you can quickly understand that the value of phi here will be twice pi minus alpha. Okay. And this upper limit for phi will be necessary for us to calculate the expression for iz. And again, I emphasize that in sharp distinction from this qz, the value of the iz which we'll be finding out next will be for the entire cross section. Okay, so let's do that. So our next job is to find iz for the cross section. Okay, so the expression for iz is equal to integration over the entire area y square dA. This is the second moment of area about the z axis, so which is why y is involved. Okay, now for our cross section, what we can do is to translate this generic formula in terms of the r and the phi and the t, just like as we had done in the case of qz. So this y will be exactly like before, where we had written it as r sine phi, and the dA, if we just take a look at the previous diagram, the dA will be for a generic little element here. So perhaps it'll be good if we draw this diagram once more to have a better understanding. Okay, so let's do that quickly. We again set up our axis passing through the center and not the centroid. So this is our y-axis and the z-axis. Unlike the previous case, we are interested in only an elemental area. So we set it up like this, a little area here. So the distance y will be again this distance, so that can be set up as r sine phi, no problem there. But what about this little area dA? This area dA, what will be that? So that will be nothing but t times ds. So maybe it will be useful to just write it down separately here. The dA will be equal to t times ds. You understand that this here is my ds, and I want to express this in terms of the r and the phi, and if you just quickly refer to our previous slide here, the ds is r d phi. So this is t times r d phi. You again note that the phi is calculated from this horizontal axis. Okay. So y will be r sine phi. Because we have a square, we put the square here, and for the dA we'll be putting t times r d phi. Now what will be the limits of integration? So we have to put the limits of integration for phi, and you note that in order to cover this entire cross section from here, starting from here, which is phi equal to alpha, as we go round and come here, it will be phi is equal to alpha to phi equal to twice pi minus alpha. So just to make this clear again, this angle here is alpha and this angle here is alpha, and because this entire angle is twice pi, so the phi will go from alpha to twice pi minus alpha. Okay, so let's do this very quickly. So the r cube will come outside. We'll have t also coming outside, and we'll have this thing. So that will be sine square phi d phi. Now we can quickly convert this to an easily integrable form in this fashion. Okay, I'll not go through the steps anymore. I'll just put down the answer here, which is half r cube t twice pi minus twice alpha. This directly comes from the integration of this 1 here, and the cos 2 phi will give me a sine 2 phi divided by 2, of course, and that will ultimately lead to a nice simplification, and it will give me plus sine 2 alpha. Okay, so I have this for my IZ. So let's take an account of what we have achieved till now as far as the steps required to find out the location of the shear center is concerned. So going back to the previous page, we see here that we have already done this step, find QZ all along the cross section. We have also just found out the value of IZ. Now we can immediately go to this expression here for sigma Sx or sigma Xs and put down the values of QZ and IZ that we have found out, and get the distribution for the sigma Sx or sigma Xs. So that's what we are going to do. Okay, so let's go to the next slide, the next page. Okay, so we'll find out the distribution for the shear stress, and let's refer to the formula once again. Okay, so we have here sigma xs is equal to sigma sx is equal to pqz divided by iz. I think I've made a small mistake here. There is a t missing in the denominator, so we should have a t here. Sorry about that. Actually, I missed it here also. There should be a t here in the denominator, but no problem. We have corrected this at the proper time. Okay, so this is pqz divided by tiz. So if we put down the values of qz and iz, what we would obtain is p times r squared t cos alpha minus cos phi divided by t, and the expression for iz was half r cube t twice pi minus twice alpha plus sine 2 alpha. Okay, so overall what we'll end up with is just this. The t from the numerator will cancel. We'll obtain p cos alpha minus cos phi divided by maybe you can take the 2 outs upstairs in the numerator, and this will be r cube, sorry, this will be just the r times t twice pi minus twice alpha plus sine twice alpha. Okay, so now that we have found out the distribution of sigma xs, we are ready to determine the torsion, the contribution that this shear stress distribution will have towards the torsional moment, and in turn how that will balance the torsional moment due to the externally applied transverse load. Now, before we can do that, it is extremely important as far as the physical understanding of the problem is concerned to realize where this shear stress distribution is actually lying. We had discussed this in the previous class while we were developing the general theory, but it will be again useful to discuss this very quickly. So let's actually draw the beam. So let's say we have the beam here, and today we are considering a circular cross section, an open-ended thin-walled circular cross section, and let's say that this beam is fixed to a wall like this, and let's say that we have applied some kind of a transverse load here. So this is a very generic representation of the transverse load. We really don't know where it is, but we do understand that this is being applied through the correct location of the shear center. So if this is the line of action here, we are guaranteed to have the shear center somewhere on this line of action. Now, as we had discussed during our general theory last time, for the purpose of carrying out the torsional moment balance, what we do is to take a cut section on this beam so that a cross section like this is so a cross section like this is exposed, what we had also done last time was to name the piece which was in front of this cutting plane. So this piece, this entire piece starting from here to here, so this entire piece lying in front of this cutting plane as our piece 1, and the one that is to its back as 2. Subsequently, what we had done was to consider this piece in isolation. So in isolation like this, where we understand this is just the piece 1, where also the externally applied load is like this. Now we understand that the shear stress distribution that we are talking about is on this hatched edge, on this hatched face. So this is the face which is at the back of the cut piece 1, flush with the cutting plane that is present here. So I repeat myself, the shear stress distribution that we are concerned with and which will contribute towards the torsional moment, which in turn is going to balance the torsional moment due to this externally applied force, that shear stress distribution, basically this shear stress distribution which you have just found, is on this. Please note that if we were to draw the section, the cut piece 2, there would be an analogous shear stress distribution, but whose orientation would be exactly opposite to the shear stress distribution orientation which would be present here. So what do I mean by that? So let's say that so this picture would be clear if we draw this looking into the x-axis. So you understand that the x-axis is oriented like this. So if we look into the x-axis towards its negative direction, the picture that we'll see there, that will help us to have a very clear-cut, explicit physical understanding. So first what I will do is draw that front view looking into the x-axis for the cut piece 1. So we go to the next page and this is the diagram that we are seeing. Now, as I had drawn earlier, let me depict the externally applied load like this. So this is my P. Now, you please note that we are talking about the cut piece 1 here. The face that we are seeing here, this face, this is the front face. Okay, so this is the front face. This front face is a free face. It will not have any shear stress distribution on it. But there is also a back face. There's also a back face which is superimposed behind this, or rather the front face is superimposed on the back face there. So if we want to draw the shear stress distribution along it, what will it look like? Now, is it going to so is it going to be oriented like this, where the arrows go in a clockwise fashion, or is it going to be in an anti-clockwise fashion? Please note again that this shear stress distribution is shown on the back face of the cut piece 1, that is the face flush with the cutting plane and in front of it. So is this the correct orientation of the shear stress? Now, the answer is yes, this is the correct orientation, because you see, only if we have such an orientation of the shear stress distribution that it will effectively contribute to a shear force which would be like this, and only if we have such a shear force distribution that the force equilibrium of the cut piece 1 will be balanced. So if you just look back at the previous thing and I draw my shear stress distribution like this, only in that particular case where the shear stress distribution on the back face of this cut piece 1 is oriented in a clockwise fashion, that it will contribute to a shear force on that back face which would be oriented upward and which would be balancing this red colored externally applied transverse force, because you understand that it is not enough for static equilibrium to have the torsional moment balanced. It will also be necessary to have the force equilibrium true. So as far as the force equilibrium along the y direction is concerned, we must have a shear force to balance out this externally applied load, and it is only through a shear stress distribution orientation in this clockwise fashion that such an upward pointing shear force will be present. But what about the cut piece 2? So for the cut piece 2, if we go to the next page, let us draw the front view looking into the x-axis for this cut piece 2. You understand that this is my cut piece 2, and this face that I'm looking at, this is the front face of the cut piece 2, which is flush with the cutting plane and behind it. So if we just take a look at the previous diagram, I'm looking at this piece 2 and I'm looking at this front face here. Okay, so what will be the orientation of the shear stress distribution? You see, this face here is touching the back face of this cut piece 1. The I repeat, the front face of this cut piece 2 is touching the back face of this cut piece 1. So the shear stress distribution there will be exactly the same but oriented in the opposite sense. So it will be anti-clockwise. And only if we have that, the shear force here will be like this. And you all know very well that that if we have such a situation, so this is my cut piece 2, and this is my cut piece 1. Then if I have a shear force acting like this here, which is balancing this externally applied, so this is then on this face I must have a shear force which is opposite but equal in magnitude to this, and this shear force, the downward pointing shear force, this is this shear force which will be actually as a resultant of the contributions from this shear stress distribution. So it is extremely important to understand this. The reason that I am emphasizing this and spending such a lot of time on this is that in many textbooks, in almost all the textbooks that I have seen, what they show is that so it's a very confusing kind of diagram. What they show is that the transverse load acting downward like this, and the shear stress distribution that they show is this kind of an anti-clockwise shear stress distribution. So which cut piece are we talking about? How is that kind of a shear stress distribution balancing this thing? That is not clear. I'm not saying that it is what is shown in the textbooks is wrong, but it is kind of very confusing. So I thought that I'd make this point very explicit and very clear. So I hope you guys understand this. So with this physical understanding, we can immediately go to the next page and do the torsional moment balance. Okay, so this is my cut piece 1. My transverse load is like this, and the shear stress distribution is like this. Now the axis about which I wish to take my torsional moment is this x-axis. Axis about which the torsional moment would be taken. Okay, so first of all, we take the torsional moment of the P. So this is our P here. We understand that it is passing through the shear center. So we understand that this distance is E from the x-axis. So the torsional moment due to P will be simply P times E, and that should be equal to the torsional moment contribution from the shear stress distributions. So how can you write the shear stress distribution contribution? So sigma xs times the area of an so when we say an area, it's an elemental area, and that's like a dA, and we have already seen that the dA is nothing but tr d phi. So tr d phi, this is the elemental area, and since we wish to take so this is like an elemental force, so this is so this part is like the dA that multiplied with the shear stress that gives us the elemental force, and we have to take the moment, the torsional moment of this about this axis, and you see what is the distance of any of these little elemental forces that will be present at any point of this cross section. So if we just extend the x-axis backwards, it will be here. So about the x-axis, the moment arm would be nothing but capital R. So this entire thing has to be calculated going from one end to the other end. So this will be, the limits of phi will be from alpha to twice pi minus alpha. Okay, so all that you have to do is substitute the expression of sigma xx that we had obtained earlier. So this this big expression that we had found out for the sigma xs, we have to substitute it there and carry out the integration. So so if we do that, what we end up with is, I'll not go through the intricate steps here, and I trust everyone will be able to do this. You see, there will be no problem with the denominator. That's just basically a constant which will come out of the integration. What will be left inside the integration will be basically the contribution which comes originally from the QZ. So so that will be just the cos alpha minus the cos theta term, and if we just do it patiently, ultimately we'll arrive at this expression. So this is twice pi twice PR times twice pi minus twice alpha cos alpha plus 2 sine alpha divided by twice pi minus twice alpha plus sine twice alpha. Now you see the beautiful thing that has happened. On the left hand side we have this P, and on the right hand side also we have the P. So as we had mentioned earlier, ultimately, even though we are making our calculations with reference to a particular transverse load like this, but ultimately the answer that we are getting for the location of our shear center, which is this distance E from the x-axis, it is purely independent of the P. So what we have finally is this thing, this P cancels and this P cancels. So this is our answer. So this E is denoting the distance of the shear center point from the x-axis. Now, one may think that what we have basically obtained is the distance of the line of action of this force P from the x-axis. But we have not really explicitly calculated the location of the shear center that would be here. Sure, we know this distance E in terms of all the given parameters like capital R and alpha, but are we really sure about where on this thing the shear center will be lying? And yes, we know that by virtue of the nice symmetry of the problem, and that will be exactly lying on an axis which is parallel to the z-axis. So the location of the shear center would be, so let's mark that out in white color. So this will be actually the location of the shear center. So E is the distance parallel to z-axis from the x-axis the y-coordinate for the shear center is 0. Okay, so ultimately what we can say is that the shear center will be located at z equal to E and y equal to 0, where the expression of E is given by this huge expression thing. Now, as interesting exercises or as further simplifications, what you can try to do is you can take different values of alpha, like you can have interesting cases where alpha is equal to pi by 2 or alpha tending to 0, and you can see what values you obtain. Please note that that I mentioned that alpha tending to 0, but not alpha equal to 0. So please do not take alpha equal to 0, because that would depict a closed thin walled section, and our theory would not be valid for that. So it is really important that we maintain our cross section to be thin walled as well as open ended, which is why you can make the alpha as small as you want, but you cannot take that to be equal to 0. So that a little slit has to be still open at the value of phi equal to alpha being very small. Okay, so that sums up our discussion regarding this example problem, and I hope some of the more intricate concepts here would be cleared through the very explicit discussion that we have had. So all right, thank you very much.